Okay, so by the end of this lesson, you'll be able to describe what inertia is and how it plays a role in motion, and determine the direction of acceleration by the net force, direction or the motion of an object, and also by the velocity versus time graph. Okay, so first off, I'm assuming at some point in your life, you have gone to a bowling alley and you or someone else that you knew did something like this. You're like, watch this slow roller. Oh, bowling lane's a little crooked here. Okay, how would you describe the motion of the ball? At a fairly constant. Okay, hopefully it's close to constant velocity. Like on a bowling lane, we try to get rid of friction as much as possible. Okay, and it rolls close to a constant speed. Okay, now I want you to remember the last time you were in space. You remember that? And you like took a bowling ball and you threw it. Remember how that worked? Okay. How would you describe the motion of the bowling ball? We're in deep outer space and you threw it, you pushed it. How would it move? How would it move? Yeah, right. Yeah, constant velocity in a straight line path. Okay, now I know we don't really experience that very often. Like, okay, so Newton's first law says an object at rest will stay at rest, an object in motion will stay in motion. We do not have a problem with objects at rest staying at rest. Like if I look at this table, it's at rest. I expect it to stay at rest. It would be really weird if that just like all of a sudden like, okay, we'd look for something that would cause that to make it not be at rest. Okay, but the thing that we have a hard time with is believing this. If something's in motion, it wants to stay in motion. Naturally, we always see things moving and then eventually what? Stop. So we think that's the default mode. Okay, but what's causing the bowling ball to slow down? What would cause objects to slow down? Gravity, friction, and one more culprit, air resistance. Okay, all three of which are examples of forces. Okay, if we could get rid of the forces, things would naturally do what they'd want to do. And if something's moving, it just wants to continue moving forever. It doesn't ever run out of energy. It's like, yes, I'm moving. I just want to keep on moving. Yes. Okay. Think of an air hockey table. Okay. That puck slides without friction. Okay. That's what looks so mesmerizing about it. Is like, dude, that just, whoa. Okay. That's what it does without forces. Like, it just wants to continue on. That's what its inertia wants to do. Inertia is the object's natural tendency to maintain its present state of motion. Okay, it's inertia. The table's inertia wants to stay at rest, and it, like I push it, and it's like, I don't like that. Okay, it wants to stay at rest. Now, the reason why it doesn't continue to move is because you have friction. Okay, but if you set something in motion in space, it's doing what it naturally wants to do. It's like, yes, I'm moving, or I just want to keep on going forever until a force acts on it to make it do something different. You all right with that? So if something's moving, it naturally, without any force required, will continue moving forever. Okay? Sorry, so that was the bowling ball demonstration. Okay, good at that. All right, so I have a fan here. Okay, if I had hair, it'd be like pretty cool looking, but you know, you have to pretend. I stick that fan on a fan cart. Sorry, I stick that fan on a cart and it becomes a fan cart. Okay, now the way that I want you to look at this is not which way this is blowing air, but which way this fan is pushing on this cart. Okay. So here, if I turn this on, tell your neighbor what's going to happen, more than just it's going to move which way, but like tell your neighbor how it's going to move. Here's some options for you. Will it move at a constant velocity? Will it speed up for a little bit and then move at a constant velocity, or will it speed up the entire time? Have a conversation.
Appears to want to roll away. The fan is moving at the same speed up. Yes.
Okay, ready? Here's the answer. Okay. It's sped up the entire time. Okay. Because it experienced a force the entire time. Okay. Once it's moving, if I turned it off, it's going to continue moving at a constant velocity. Why? Inertia. That's what it naturally wants to do. It's moving. It's like, yes, I'm moving. Let's keep doing this. But if it experiences a force, it's like, dude, what? And it's like keeps on speeding it up. Experiences a change in motion. Experiences acceleration. Which way was it experiencing acceleration? In the positive direction or in the negative direction? Positive direction. Two different reasons. Number one, it experienced a force. Which way was it being forced? In the positive direction. Whatever. Okay, this is you can take this to the bank. This is an always. The direction of acceleration will always be in the direction of the total force. Okay, the direction of acceleration will always be in the direction of the total force because the total force causes acceleration. Its inertia wants to do whatever it's doing. Like if it's at rest, it wants to stay at rest. Did that started at rest, correct? Did it stay at rest? No. Why not? Because something on the outside says do something different. It's like, oh man. And so it experienced acceleration in that direction. Now, once it's moving, it wants to continue moving, specifically at a constant velocity. Did it maintain a constant velocity? Nope. Why not? Still getting forced. Like, ah! Okay. So it always experiences acceleration. Okay. The second way you can explain the direction of acceleration is which way was it moving, in a positive or negative direction? Okay. If we don't like voice boxes, we can do fingers. Which way was it moving? I need some engagement here. Show me there's some kind of life out there. Okay. Was it speeding up or slowing down? Speeding up. So if it is speeding up, then the sign of acceleration, the direction of acceleration is going to be the same as the sign of velocity. You okay with that? So if you're speeding up, the sign of acceleration is the same as the sign of velocity. Okay. Now, what about this? Okay. Which way was the force acting on it after I let go? Okay, let me throw this out at you. Okay, I'm going to take this off. I'm just going to push it. After I get done with it, am I exerting a force on that? Be really cool if I could. It'd be like I was a Jedi. Once I let go of it, I no longer exert a force. So why is it moving? Is there a force going in that direction? Nope. It's moving. It just wants to continue moving. Good with that? So after I let go of it, what's the direction of the force? What's the direction of the force after I let go of it? Show me. After I let go of it, the force from the fan was going this way. It was moving this way. That's not a force. I already, like, it's just one and two because of its inertia. Going that way. What's the direction of acceleration? Also in the direction of force, like always in the same direction as force, that way. Okay. Was that moving in the positive or negative direction? Negative direction. Was it speeding up or slowing down? Slowing down. If it is slowing down, then the sign of acceleration is the opposite of the sign of velocity. It had a negative velocity, slowing down, therefore it has a positive acceleration. Okay? There's two different ways to look at the direction of acceleration. Look at the force, or look at the motion in terms of is it speeding up or slowing down. Okay? This whole lesson is devoted to learning the direction of acceleration. It is not as simple as velocity and displacement. With displacement and velocity is like, I'm going in the positive direction. That's a positive velocity and a positive displacement. I'm going this way. Oh, that's a positive. That's a negative velocity and a negative displacement. That's pretty cut and dry. Acceleration, it's a little hard than that. Good. Okay. How are we doing so far? Okay. So, just talking about that. Same sign as acceleration. Sorry, direction of force is the same as the direction of acceleration. Give that one a shot. Talk to your neighbor. Correct answer is B. Good job. Okay, we're moving in the positive direction and we're slowing down. Therefore, the direction of acceleration is the opposite of velocity, negative direction. In order for her to slow down, which way is the force acting on her? In the opposite direction of motion. Because her inertia wants to continue moving at a constant speed, straight line path. To make her slow down, you have to experience a force going that way. Therefore, the direction of acceleration is also in the negative direction. Tell your neighbor. Tell them why.
If it was slowing down. Still be negative. Speeding up.
Okay. Correct answer is B. Let me destroy, in case it hasn't been destroyed already, a popular misconception. Ready for this one? Most everybody's belief prior to taking physics and having this corrected is if someone says, oh, you have a positive acceleration, you think you're speeding up. And they're like, oh, you have a negative acceleration. That probably means you're slowing down. That is not always the case. Do not assume positive acceleration means speeding up. Do not always assume a negative acceleration means slowing down. Sometimes that's the case, but not always. Okay. Good with that? So if you like, that's a popular misconception. Okay, kind of talked about that. Look at the force, same direction of the force. Force causes acceleration. Second way, if it's speeding up, the sign of acceleration is the same as velocity. If it's slowing down, the sign of acceleration is the opposite of velocity. Okay, two ways to look at it. Have a conversation. Correct answer is, good job, A, positive. You are moving in the negative direction and slowing down. Therefore, the sign of acceleration has to be the opposite of velocity. So positive. In order to slow down, Wile E. Coyote natural inertia wants to continue moving in a negative direction at a constant velocity. To make them slow down requires a force in the opposite direction that they're moving to make them slow down, and acceleration has that same direction. How are we doing? Oh, nope, we need to do this one. Okay. So I want you to evaluate this. After I let go of it, okay, I want you to show me with your finger. I'm gonna break it into phases here. Show me with your finger the direction of acceleration. After I let go of it, the direction of acceleration. Show me. After I let go of it, the direction of acceleration during that phase, you are slowing down while you move in a positive direction. So you have a negative acceleration. The fan is pushing it this way, causing it to slow down. Good with that? Now, this phase. What is the sign of, what is the direction of acceleration? Show me with your finger. You're speeding up in the negative direction. So the sign of acceleration is the same as velocity. The force acting on the cart is this way. Good with that? Okay. Now I'm going to put it all together. Show me step by step which the direction of acceleration is after I let go of it. The whole time? Why? Yep. It slows down the moment I let go. There's always a force acting on the same direction. What about, okay, check this out. How would you describe how fast it's going right there. How fast was it going? Like, what was going on as it moved this way? Slowing down. Until what point? Stops. What? So how fast was it going? 0. Did it still have acceleration? How long was it going 0 meters a second? Just a moment. The moment right beforehand, which way was it going? Which way was it moving? The moment right afterwards, which way was it moving? So was the velocity changing from moment to moment to moment? Do you have acceleration? Yes. Was the force always acting on it? Yes. Was it doing what inertia wants to do at any point in time? It was always changing. Therefore, always experiencing acceleration. How are we doing with that idea? Okay. Thumbs up when you have a guess. Have a conversation. What do you say? You got one vote for A. That's it. A. Okay. So mathematically, change in velocity. Okay. Final minus initial. So your final velocity is in negative 3 meters per second. Your initial velocity is plus a positive 3 meters a second. I don't require you to do the positive here, but I'm just trying to teach something there, just to be explicit with that. So negative 3 minus positive 3 is a negative 6. Okay, that's mathematically. Conceptually, here's the idea. As the squirrel is going in the positive direction here, at some point it has to, in order to go back the other way, what does it have to do? Slow down, stop, and turn around. So during the slow down and stop, I'm moving in the positive direction, but I'm slowing down. Therefore, the sign of acceleration is negative. And then when I speed back up in the negative direction, what is the sign of acceleration? Still negative. Even if that happens abruptly, even it's like boom, like at some point, if you slow motion that, is like slow down, stop, turn around, speed up. You all right with that? Okay. The math and the concepts always have to agree. If you're understanding conceptually and you're understanding mathematically are in conflict with each other, not a good scenario. Okay. Have a conversation. What do you say? Got threes on the table. Anybody else want to weigh in? Okay. Let's. This is I really like this question a lot. Like this really like brings out some good conversations. Okay. So, do they have to be going in opposite directions? Is it possible for the stallion to be traveling in the positive direction and yet still have a negative acceleration? Yes. What would be happening to the stallion if he was traveling in the positive direction but had a negative acceleration? Slowing down. Okay. Could the mare also be going in the positive direction? Yes. What would she be doing? Speeding up. Okay. Um, so if the stallion is going in the positive direction and has a negative acceleration, how would you describe his motion? Slowing down. If he continued to have that same negative acceleration, what eventually is going to happen? Stop and then turn around and go fast, like speed up in that direction. Okay. At some point, though, the stallion has to stop. The mare most likely will be going faster than zero at that moment in time. Possibly could be going zero at that same moment in time, but definitely not a have to. Okay, so B is out. All right with that. Okay, so that knocks out C. The stallion is slowing down. If the stallion was going in the negative direction, how would you describe the motion of the stallion? Speeding up or slowing down? Speeding up. Okay, and the mare could be going in the negative direction and slowing down. E is the correct answer. Okay. Learn some stuff. Okay. All right, switching gears. Tell your neighbor and tell them why. Correct answer is? Okay. So we'll look at this a couple different ways. So graphically, what on a velocity versus time graph tells us acceleration? Slope. How do you describe the slope of that blue line? Is it positive or negative? Okay. So in math class, when we did this, is that a positive or negative slope? Positive. Okay. It does not matter what quadrant it's in. Right? It's a positive slope. Here, we're just looking at the first and the fourth quadrant. Okay. Has a positive slope. Therefore, the value of acceleration is also positive. Okay. From a story point of view, from a motion point of view, how would you move to make this graph? Slow down traveling in which direction? In the negative direction. So you're slowing down traveling in the negative direction. Therefore, you have to have a positive acceleration. And just a little side note, acceleration versus time graphs in this class will always be horizontal lines. So we're assuming a constant acceleration. Do that. Tell your neighbor. Correct answer is C, because they're parallel lines that have the same slope. Next question. Okay, I want you to tell your neighbor the answer, but first time just based off graphically. Like looking at the graph, how do you know? Tell your neighbor. Okay, now I want you to tell your neighbor why the right answer is the right answer based upon how you would move to make the blue graph. Correct answer is A. You have a negative slope the whole time. You're slowing down in the positive direction, negative acceleration, and then you're speeding up in the negative direction, still a negative acceleration. This is the same thing. This would produce that graph. Get that? Okay. Making sense? Are we like, how's confidence rating? How are we doing here? 5 rocking it out, 0 crying in that corner. Wishing I'd chosen anatomy or physiology or something like that. Last question. Tell your neighbor. Correct answer is C. You have a positive steep slope. You're speeding up quickly in the positive direction, and then you're slowing down in the negative direction, not as quickly. Okay, got a worksheet due tomorrow.